In the infinite, silent tapestry of the cosmos, appearances are often the most dangerous deception of all. As humans, we are programmed to look for familiarity in the dark. We scan the stars for patterns, for shapes, and for colors that remind us of where we came from. We yearn to find a reflection of ourselves in the void. If you were an interstellar traveler, drifting through the constellation of Vulpecula, the little fox, about 64 light-years from Earth, you might stumble upon a world that stops you in your tracks. From a distance, it is breathtaking. It hangs in the void like a deep cobalt marble, swirling with serene shades of azure and royal blue, interspersed with wispy streaks of white clouds that look invitingly calm. To the human eye, conditioned by thousands of years of evolution on Earth, it looks like a sanctuary. It looks like water. It evokes the image of the pale blue dot that Carl Sagan famously described, a symbol of life and fragility. It looks like home. It whispers a promise of oceans, of rain, and of life. But this planet, catalogued by our astronomers as HD 189733b, is not a second Earth. It is not a water world. It is, in fact, one of the most hostile, violent, and unforgiving environments we have ever discovered in the Milky Way galaxy. It is a place where the laws of weather have been twisted into a horror story that defies comprehension, a siren that lures you in with beauty before revealing its teeth. On this world, the wind doesn't just blow. It screams at 7 times the speed of sound, creating shock waves that ripple through the atmosphere with the force of a nuclear blast. The heat is not just tropical. It is an inferno intense enough to vaporize rock into mist. And the rain? It doesn't rain water, it rains molten glass. And because of the ferocious supersonic winds, it rains glass sideways. Welcome to HD 189733b, the beautiful nightmare. Today, we are going to take a journey to this alien hellscape. We will dissect the physics of its impossible storms. We will understand the incredible detective work, the spectroscopy and thermal mapping that allowed us to map its weather without ever seeing it directly. And we will explore what this hot Jupiter teaches us about the chaos of planetary formation. To understand the monster, we first have to understand the cage it lives in and the violently close relationship it shares with its parent star. A planet is defined by its star, and in this case, the relationship is abusive. HD 189733b orbits a star known simply as HD 189733. It's a K-type orange dwarf star, slightly smaller, cooler, and dimmer than our own sun. But don't let that fool you. While it may be cooler than the sun, this star is far more volatile. It is an active star, effectively a teenager in stellar terms, prone to massive star spots covering significant portions of its surface and violent outbursts of X-ray radiation that bombard anything in its vicinity with sterilizing energy. And our planet is not just in the vicinity, it is practically hugging the star. In our solar system, there is a clear, polite order. Rocky planets like Earth, Venus, and Mars stay close to the warmth. The gas giants, Jupiter, Saturn, Uranus, Neptune, live in the cold, dark outer suburbs. For decades, astronomers believed this was the standard blueprint for all planetary systems in the universe. We thought nature followed rules, keeping the giants far away from the hearth. But HD 189733b broke the mold and shattered our expectations. It is a gas giant, about 13% more massive than Jupiter, yet it orbits its star at a suicide distance, just 3 million miles. To put that in perspective, Earth sits a comfortable 93 million miles from the Sun. Even Mercury, the scorched inner planet of our system, is roughly 36 million miles away. This blue giant is 10 times closer to its star than Mercury is to the Sun. It is so close that the gravitational interaction is immense, locking them in a tight embrace. It completes an entire year, a full orbit, in just 2.2 Earth days. If you lived there, you would celebrate a birthday every 53 hours. This class of planets is known as hot Jupiters. When they were first theorized, many scientists thought they were impossible, arguing that a gas giant couldn't form that close to a star without being destroyed or migrating outward. Yet, here they are, cosmic paradoxes that shouldn't exist, yet do, challenging our models of how solar systems are built. But how did we find it? We didn't see it with a telescope in the traditional sense. You cannot simply point a lens at a star 64 light-years away and snap a photo of a planet. The glare of the host star is millions of times brighter than the planet itself. It would be like trying to spot a firefly hovering next to a stadium floodlight from 10 miles away in heavy fog. Instead, we used the transit method combined with radial velocity measurements. Imagine a moth flying in front of a lighthouse beam. For a brief second, the light dips. That is what happened in 2005. Astronomers watched the star HD 189733 and noticed a periodic dip in brightness, a tiny shadow crossing the face of the star every 2.2 days. The shadow was deep, blocking about 3% of the star's light. This told us two things. The object was massive, and it was incredibly close. But HD 189733b is special among exoplanets. Because it blocks so much light and is relatively close to Earth, it became the perfect laboratory. It is arguably the most studied exoplanet in history. We have pointed the Hubble Space Telescope, the Spitzer Space Telescope, and ground-based observatories at it, peeling back its layers one by one through a process called transmission spectroscopy, analyzing the starlight filtering through the planet's atmosphere to read its chemical fingerprint. And as the data started coming in, the picture shifted from a simple gas giant to something far more sinister. Let's return to that color, the deep blue. The color that tricks our minds into thinking of tranquility, coolness, and depth. When we look at Earth from space, we see blue because of our oceans absorbing red and green wavelengths of light, reflecting the blue back to our eyes. We also see the scattering of sunlight by nitrogen and oxygen in our atmosphere, a phenomenon called Rayleigh scattering. It's the same reason our sky is blue. When astronomers first analyzed the light spectrum of HD 189733b using the Hubble Space Telescope's imaging spectrograph, they measured the planet's albedo, its reflectivity. They found that the planet appears a deep, dark blue, remarkably similar to the color of Earth's oceans during a storm, or perhaps the deep azure of Neptune. It stands in stark contrast to the reddish hue of its parent star. Naturally, the human mind jumps to water. Could there be a super ocean hiding beneath those clouds? Could this be a water world covered in a global sea, teeming with exotic aquatic life? The answer is a definitive, crushing no. The temperature of the planet's upper atmosphere hovers around 1,000 degrees Celsius, or over 1,800 degrees Fahrenheit. At these temperatures, liquid water is physically impossible. It would flash boil into steam instantly. Even water vapor would struggle to exist without being thermally ripped apart into its base atoms of hydrogen and oxygen. The bonds that hold water together simply cannot survive this furnace. So, if it's not water, what is painting this planet blue? The answer lies in a substance you probably have in your kitchen or on your windows right now: silicates. Essentially, sand and glass. The atmosphere of HD 189733b is thick with clouds, but they aren't made of soft water vapor. They are high-altitude hazes composed of tiny particles of magnesium silicates. These particles are incredibly small, smaller than a micron. And just like the nitrogen molecules in Earth's sky scatter blue sunlight to give us a blue day, these silicate particles are the perfect size to scatter the intense blue light from the orange dwarf star while absorbing the red light. It is a cruel cosmic irony. The universe has taken the ingredients of a desert, sand, and heat, and used them to create an illusion of a water world. It is a planet camouflaged as a paradise, wearing a mask of beauty. Furthermore, unlike the blue of Neptune or Uranus, which comes from methane-absorbing red light in a freezing atmosphere, the blue of HD 189733b is born of fire. It is the glow of a glass atmosphere reflecting the fury of a nearby star. Once you descend past that blue haze, you enter an atmospheric engine driven by pure violence, where the beauty quickly fades into terror. To understand the weather here, we have to look at its rotation, or rather, the lack of it relative to its star. This determines the rhythm of life, or death, on the planet. Because the planet is so close to its star, the immense gravitational pull has slowed its spin over millions of years. It has become tidally locked. This means the planet rotates on its axis at the exact same speed it orbits the star. The result is a permanent dichotomy, a world split in two. One side of the planet faces the star forever, an eternal, scorching day where the sun is locked in place, never rising, never setting. The other side faces the freezing void of space, an eternal, pitch-black night. There is no twilight, no dawn, just a fixed, massive, burning eye that never blinks. This creates a temperature gradient that is hard for the human mind to comprehend. The substellar point, the spot directly under the star, is being baked at temperatures exceeding 2,000 degrees Fahrenheit. It is constantly bombarded by radiation, acting like a permanent wound on the planet's face. Meanwhile, the night side should theoretically be freezing cold, dropping to hundreds of degrees below zero, as it hasn't seen sunlight in eons. But when astronomers used the Spitzer Space Telescope to create a thermal map of the planet, the first ever weather map of an alien world, they found something strange. The night side wasn't freezing. It was still incredibly hot, around 1,200 degrees Fahrenheit. How is this possible? How does the side facing deep space stay hot enough to melt lead? The answer is the wind. The atmosphere of HD 189733b is a global conveyor belt of heat, a mechanism the planet uses to survive. The air on the day side is superheated, expands violently, and rushes toward the cooler night side to equalize the pressure. But this isn't a gentle breeze or even a trade wind. We are talking about a super-rotating equatorial jet. Winds here move at 2 kilometers per second. That is roughly 4,500 to 5,400 miles per hour. Let's pause and visualize that. The strongest tornado ever recorded on Earth had wind speeds of roughly 300 miles per hour. A Category 5 hurricane sustains winds of 157 miles per hour. The speed of sound on Earth is about 767 miles per hour. The winds on HD 189733b are nearly 20 times faster than the strongest winds Earth has ever produced, and 7 times faster than the speed of sound. The kinetic energy in this wind is devastating. If you were standing on a hypothetical platform in the clouds, the wind wouldn't just push you. The sheer force of the air molecules hitting you would act like a solid wall, pulverizing you instantly. And this wind does something fascinating to the planet's hot spot. On most planets, The hottest point is directly under the Sun at noon. But on HD 1897333b, the winds are so fast that they actually push the heat itself. The thermal map shows that the hottest point of the planet is shifted to the east, dragged along by the supersonic jet stream. This is a world where the weather moves faster than the planet itself can adjust. It is a storm that never ends, encircling the entire globe, screaming through the silence of space. Now, we arrive at the most famous and most terrifying feature of this world: the precipitation. The weather forecast here is unlike anything in the solar system. On Earth, the water cycle is gentle. Water evaporates, forms clouds, condenses, and falls as liquid rain. It nourishes life, fills our rivers, and cools our air. On HD 1897333b, we have a silicate cycle. On the scorching day side, temperatures are hot enough to vaporize silicates. Rocks, minerals, and glass are turned into gas, mixing with the atmosphere. It is literally hot enough to evaporate a mountain. But as these high-speed winds rush this vapor toward the night side, the cooler side, the temperature drops slightly. Just as water vapor condenses into droplets when it cools, the vaporized rock condenses. It transitions from gas back to liquid droplets, and then to solid. High in the atmosphere, clouds of magnesium silicate form, but they don't stay as soft, fluffy clouds. The particles grow larger, fusing together through a process called nucleation. They crystallize. They become glass. And then, gravity takes hold. It begins to rain. But remember the wind. The gravity of the planet is trying to pull the glass down, but the ferocious 5,000-mile-per-hour winds are whipping it sideways. Imagine a storm where the rain doesn't fall down. It flies horizontally, and the raindrops are not water. They are jagged, microscopic shards of molten glass. To be caught in this storm is to be caught in a planet-sized sandblaster. It would be a death by a billion cuts. The air itself is a weapon. This sideways glass rain scours the atmosphere, shredding anything complex enough to exist there. It would strip the flesh from bone and the paint from metal in milliseconds. The sound would be unimaginable. It wouldn't sound like rain on a tin roof. It would sound like a continuous, deafening shriek. The friction of glass moving at hypersonic speeds, colliding with the denser layers of the atmosphere. It is the scream of a billion particles tearing through the sky. This isn't just a weather event. It's a physical assault. A sensory overload of terror involving the howling of supersonic winds, the blinding heat, the oppressive gravity, and the relentless horizontal barrage of razor-sharp matter. It is a blender the size of a planet. Let's conduct a thought experiment to truly grasp the scale of this nightmare. Let's imagine we have an indestructible probe, or a futuristic suit that can withstand these conditions, and we are dropping it into the atmosphere of HD 1897333b. As you approach the planet from space, the blue marble grows until it swallows your entire field of vision. The first thing you notice is the lack of surface features. It is a thick, opaque haze, hiding the chaos below like a heavy curtain. As you pierce the outer atmosphere, the silence of space is replaced by a low rumble. This rumble quickly escalates into a deafening roar as you hit the jet streams. The winds here are already faster than any jet fighter on Earth, tossing you like a leaf in a hurricane. You lose all sense of up and down. You find yourself on the Terminator line, the twilight zone between the eternal day and eternal night. The sky above is a gradient of deep violet fading into an angry, glowing orange. Suddenly you are struck, not by one object, but by the atmosphere itself. You are buffeted by the sideways rain. The sound of glass shards hitting your hull would sound like static on a radio, turned up to a volume that rattles your teeth. Tick, 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 millions of impacts per second, etching away at your shielding. As you sink deeper, the light fades. The thick clouds block out the star, but it is not dark. The atmosphere itself begins to glow with thermal radiation. The blue fades into a dull, hellish red, then a blinding white. Massive lightning bolts, generated by the friction of silicate clouds, might arc across the sky, lightning that strikes not the ground, but travels horizontally for thousands of miles, illuminating the glass storm. The pressure mounts. HD 189733b is a gas giant. It has no solid surface to stand on. There is no ground to catch you. The atmosphere just gets thicker, denser, and hotter. It feels like the planet is hugging you to death. Eventually, the glass rain would stop. Not because the storm is over, but because you have gone so deep that the heat melts the glass back into liquid and then into gas. You are now swimming in a supercritical fluid, a state of matter that is halfway between a liquid and a gas, glowing white hot. The pressure here is millions of times greater than Earth's atmosphere. You would be crushed into a speck of matter, indistinguishable from the planetary core. This is a world that offers no mercy. It is a world designed to destroy, layering death upon death. But even this monster has a predator. In the cosmic food chain, the star always wins. While the planet rages with its glass storms, it is slowly being eaten alive by its own parent star. The relationship between host and planet is parasitic. In 2013, the Hubble Space Telescope observed something incredible happening to HD 189733b. Using ultraviolet spectroscopy, astronomers saw a massive plume of neutral hydrogen gas trailing behind the planet, much like the tail of a comet. This tail stretches out for millions of miles into space. Because the planet is so close to the star, it is bathed in intense X-ray and extreme ultraviolet radiation. This radiation hits the upper atmosphere with enough energy to heat the gas molecules to the point where they can escape the planet's gravity. It creates a phenomenon called photo-evaporation, or hydrodynamic escape. We estimate that HD 189733b is losing mass at a rate of up to 600 million kilograms per second. Every second, an amount of mass equal to a small mountain or a large pyramid is ripped away from the planet and cast into the void. The star is stripping the planet bare, peeling it like an orange. Over eons, this planet is slowly evaporating. It is a puffy planet, its atmosphere swollen by heat, making it easier for the star to blow it away. It raises a fascinating existential question. What will be left in the end? Will the planet eventually evaporate entirely, leaving nothing behind? Or will the gas be stripped away to reveal a rocky, molten core, a theoretical type of world astronomers call a Chthonian planet, a dead, roasted husk of what used to be a giant? For now, the planet endures, but it is a temporary equilibrium, a violent dance of destruction between the gravity holding it together and the radiation tearing it apart. It is a dying world, screaming into the void as it dissolves, a victim of its own location. So why do we care? Why do we spend billions of dollars, build massive space telescopes like James Webb and Hubble, and dedicate thousands of human hours to studying a place we can never visit? A place that would kill us in a microsecond? Because HD 189733b teaches us humility. For a long time, we thought our solar system was the standard, We thought solar systems were neat, orderly places with rocky planets in the middle and gas giants on the edges. We thought that if a planet looked blue, it might hold life. We projected our own existence onto the universe. HD 189733b shattered those assumptions. It proved that planetary systems can be chaotic, violent, and utterly alien to our experience. It showed us that Earth-like in color does not mean Earth-like in nature. It proved that the universe is far more creative and far more terrifying than we dared to imagine. It expanded our imagination of what a planet can be. It forces us to refine our definition of habitable. When we hunt for life in the universe, we look for the Goldilocks zone and the pale blue dot. But HD 189733b is a deep blue dot, and it is lifeless. It serves as a warning. Do not judge a planet by its cover. As we continue to discover thousands of exoplanets, some made of diamond, some covered in lava oceans, some orbiting 3 stars at once, HD 189733b remains a milestone. It was one of the first to give up its secrets. It was the first to show us its true colors. It was the first to let us map its weather. It is a laboratory of extremes. By understanding the physics of this nightmare, we better understand the physics of our own weather, our own atmosphere, and our own precious, fragile position in the galaxy. It highlights just how narrow the parameters for life truly are. From 64 light-years away, it sits there, a silent blue jewel in the darkness of Vulpecula. It is a reminder that the universe is not designed for us. It is vast, it is violent, and it is beautifully indifferent to our existence. It does not care if we live or die. It only follows the laws of physics. We live on a rare oasis, a planet where the wind is a breeze, not a shockwave, where the rain washes us clean rather than shredding us to pieces, where the sun warms us rather than boiling our atmosphere away. We often take the stillness of our world for granted, forgetting that chaos is the norm in the cosmos. HD 189733b is the hell that helps us appreciate our heaven. It shows us how lucky we are to have a magnetic field that protects us, an atmosphere that nurtures us, and a distance from the sun that keeps us safe. So the next time you look up at the night sky, towards the constellation of the Fox, remember that out there, in the silence, a storm is raging. A storm of glass and fire that has been screaming for billions of years, and will likely scream for billions more. Thank you for joining us on this journey into the deep blue nightmare. If you enjoyed this deep dive into the cosmos, there are thousands of other strange worlds waiting to be explored. Which planet should we visit next? The world with burning ice? The planet made of diamond? Or perhaps the dark worlds drifting alone in the void? Let me know in the comments below. Don't forget to subscribe and hit the bell icon so you never miss a departure. Until next time, keep looking up.